Hey guys, welcome to our lecture for 7.5, multiple angle identities. So this whole section is going to be a bunch of different angle identities, similar to the sum and difference angle identities that we talked about in 7.4, but we've got double angle identities, half angle identities, power reducing identities, and some other ones. We are going to skip a big chunk at the very end of this because I quite frankly want to. But we're going to start with some things that are kind of crucial and important. And this first one here, these are what we call our double angle identities. Okay. As you can see here, these are when we have our angle being doubled. Okay. Quick note, if something's being quadrupled, say like for x, we can always think of that as something being doubled, right? If something, say, to the 10th, right, or 10x, right, we can manipulate things so that they are a double angle identity, can be applied. And so that is something that we want to keep in mind. And so very simply, our double angle identities, we have sine of 2u is 2 times sine of u cosine of u. Now this is actually something we saw in the last section when we did cosine of, I believe it was 2x, and we used the angle addition. So 2u, or 2x in that case, is really just x plus x. So sine of u plus u. Then using the angle sum identity, we were able to create this and get 2 sine u cosine u. Tangent of 2u is very simple. And it also uses just the same idea of angle sum, and we get this. Cosine, however, this gets a little trickier, and you may be kind of wondering, how is all of these true? And quite frankly, I don't really want to show them. I don't want to derive all of these for you. The first one here is using just the simple angle identity formula. So we end up with cosine squared u minus sine squared u. Because if you remember, cosine of u plus v was cosine of u times cosine of v minus sine of u sine of v. And if u and v are the same, as in this case 2u, so we'd have u plus u. We have cosine of u times cosine of u, it's cosine squared, sine u, sine v, and go from there. Now, the way we get the other two is just utilizing the Pythagorean identity. So sine squared u is 1 minus cosine squared. Distribute the negative because mine, and then similarly for the last one, cosine squared, and so go from there. The trick with these, sine and tangent are easy because we only have one formula, not a big deal. The trick with the cosines is identifying which form we want to use. But what's really important to recognize is anytime we have, if we're going backwards, right? This is more so going from the right side of these equations, kind of these sides over here, to these sides over here. And if we're doing that, we're just kind of looking to see if we have sines or cosines squared involved in the same situation, and kind of what we have. Notice these bottom two look very similar to some potential Pythagorean identity stuff, but there's that 2 there, that 2 cosine squared or that 2 sine squared, and that messes things up. If you see that, that's a big red flag to use double angle identities. So let's actually apply these. So given this triangle, we want to find the exact values of sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. So we can easily find sine, cosine, and tangent of theta here, and let's do that really quick. Okay, so sine of theta is opposite over hypotenuse, so that is our lovely 4/5. Cosine of theta is going to be adjacent over hypotenuse, or 3/5. And tangent of theta, opposite over adjacent, or 4/5. Okay, or sorry, not 4/5, 4/3. So now using that in these formulas, okay, we can find sine of 2 theta by simply following this formula, which is sine of 2 theta is 2 sine of theta cosine of theta. So it's 2 times 4/5 times 3/5, which ends up being 24/5. Sorry, 25th. 24/25. Right? It's really not that challenging. And if we do well, let's do tangent. Tangent of 2 theta. Well, that's just 2 tangent of theta over 1 minus tangent squared theta. Since tangent theta is 4/3, it's just 2 times 4/3 over 1 minus 4/3 squared, 8/3 over 1 minus 16/9, and that simplifies to a lovely negative 24/7. Now you may actually look at this and now go, oh, I know what cosine of 2 theta is. And that's absolutely correct. You could easily figure out what cosine of 2 theta is because we know sine of 2 theta and tangent of 2 theta. But let's use our formula to figure this out. Now, which of these three formulas do I want to use? Personally, I want to use ones that do the least amount of trig function work. Because if I accidentally made a mistake in calculating, let's say, my sine or my cosine or something like that, I don't want to perpetuate that if I can. So I want to try and kind of keep it simple. So instead of using that first one, I'm going to use the third one because why not? They're all the same. It really doesn't matter which one you use, but we end up with cosine of 2 theta is equal to 1 minus 2 sine squared theta, which is just 1 minus 2. Sine is 4/5, so 4/5 squared. 1 minus 2 times 16/25, which is 1 minus 36/25, which ends up being negative 7/25. Wait. Helps if I do things right. Yep. Okay. There we have it. So again, just like the last section, we're really just plugging in, like just evaluating these things. Really simple. We're just plugging into this formula that we have here. Again, these are not formulas I want you to memorize. I want you to have these on. These are on that formula sheet. Have them out with you. Be working on them that way. Do not try and memorize these. It's just not worth it. So now we want to find exact solutions to the equation 2 cosine x plus sine of 2x equals 0 on the interval from 0 to 2 pi. Now, what we want to do here is we want to figure out how we are going to deal with this problem. The biggest issue here is that the cosine is by itself. It's a cosine of x. Sorry, it's not by itself, but inside the angle is. But with sine, we've got 2x. So we want to use these double angle identities to split this so that we get 2 cosine x plus 2 sine x cosine x. 2 cosine x plus 2 sine x cosine x, and then that's equal to 0. The reason we want to do that is because now I can do something that's really nice. I can factor. And if we look at these, there's a 2 cosine x in both of these things. So I'm going to factor that out. So give me give me 2 cosine x times 1 plus sine x equals 0. Now, what I have here is I have 2 cosine x and I have 1 plus sine x. And I need to identify when those two things are equal to 0, when either one of those two things is equal to 0. Because since those are being multiplied, their product will only equal 0 when one of those two things equals 0. So really what I'm trying to find is I am trying to find when is 2 cosine x equal to 0 and when is 1 plus sine x equal to 0. So I'm trying to figure out when cosine of x equals 0 and when sine of x is equal to -1. Now, these should be fairly straightforward and simple. Grab your unit circle, look at these, right? These should not be a big challenge anymore. Hopefully you guys are understanding how to solve equations like this. And so what we get from cosine x equals 0 is we get that x is equal to pi over 2 or 3 pi over 2. And when sine of x equals -1, that happens when x equals 3 pi over 2. So that means when x is 3 pi over 2, both of these pieces equal 0. And so 0 times 0 is still 0, so that's fine. So really our final answer is that x equals pi over 2 and 3 pi over 2. Gives us our solutions. For this function, for this equation. And that's it. Pretty easy. All right. Now, find exact values of sine 2 theta, cosine 2 theta, tangent 2 theta, given that we know this value of sine theta, and we know that theta is between pi and 3 pi over 2. Now, that's really weird, right? Why are we looking at, we've talked about like theta being from 0 to 2 pi and stuff like that. But if we think about this, if we think about our unit circle, right? This right here is pi, and this right here is 3 pi over 2. So if our angle theta is between these, all that's really saying, this is the same as saying that theta is in quadrant 3. Okay. So that's all that's saying, right? Let me erase that. That's fine. So let's figure out what we need to know. What I know is that I have some angle. Now I'm going to give myself something like this. And I know that sine is -2 over root 13. So we can think of this right here as -2. That's root 13. I need to figure out what this value here is. Okay. To do that, just use the Pythagorean formula, which says that a squared plus b squared equals c squared. So we have that -2 squared plus b squared equals c squared. So I get 4 plus b squared equals 13. Subtract 4 from both sides. B squared equals 9. B equals 3, right? Square root both sides. And since b is a distance, not just a number, we're using +3. But then because we're in the third quadrant, that's actually going to be -3. Okay. So what that tells me then is that tells me that cosine of theta is -3 root 13. And tangent of theta is -2. Oh, just kidding. Is 2 over 3. So now that we know these, we can easily find sine, cosine, and tangent of 2 theta. So sine of 2 theta is 2 sine theta. Cosine theta, that's 2 times negative 2 root 13 times cosine theta, which is negative 3 root 13, which that equals 12 over 13. Don't know why I did that so big. 12 over 13. All right. Now let's do tangent. Tangent of 2 theta. And just following the formula, right? Keep this simple. We don't want to overcomplicate our lives. So that means that this is 2 tangent of theta over 1 minus tangent squared of theta. We have 2, tangent was 2/3 times 2/3 over 1 minus 2/3 squared. Do some fancy mathematics, simplify that, we end up with 12 fifths. Last but not least, cosine 2 theta. Now, last time we did cosine, we decided to use the version that gave us, that was, let's go up here, 1 minus 2 sine of theta, sine squared theta. Let's just use the very first one, cosine squared u minus sine squared u. Okay. So cosine of 2 theta is just going to be, very simply, cosine squared u, in this case theta, minus sine squared theta. Now you may think, hey, if sines and cosines that and they're squared, that means it's Pythagorean identity. This is 1, but remember that's sine squared plus cosine squared. So because these are subtraction, that doesn't hold up, and we can't just rely on that. So we just plug in the values. We know that cosine theta is negative 3 root 13. So we get negative 3 over root 13 squared minus sine is negative 2 root 13 squared. We do some fancy dancy mathematics. We get 9 over 13 minus 4 over 13, and that comes to a lovely 5/13. And there you have it, right? So again, relied on kind of doing this right triangle trig stuff, figuring this out, okay? And then just applying the formulas. Nothing too crazy or scary. So let's look at example 4 here. Rewrite the following using double angle formulas, okay? So what this means is we need to rewrite these either by applying a double angle formula, so taking something that is a double angle and writing it as the single angle, or taking something that has already been split and sucking it back in as writing it as a double angle. And the way we know which way to go is very simply by identifying whether the angle is a doubled angle or not a doubled angle. We look at this first example, A, sine of 46 times x. We're like, well, that's not a double angle, but it's also not a single angle. But if you remember what I said at the very beginning, if we had like 10x, that could be written as 2 times 5x. So this is just equal to sine of 2 times 23x. And so then if I apply the double angle formula for sine, this becomes 2 sine of 23x times cosine of 23x. Now 23x is an odd number, so I can't write that as like 2 times something, right? And you may be like, but we can, right? We are not going to write this as 2 times 16.5x. Just no. We're not going down that rabbit hole. Unless it can be written split as an integer, don't try and split it. It's just not necessary. Now B, I'm looking at this and I'm seeing, okay, so I've got 4 minus 8 sine squared x. What am I doing? Well, I don't have a fraction at all, so I'm definitely not using tangent. I'm not using tangent at all, so it's definitely not tangent. So I'm thinking it's either sine or cosine because it's not tangent, but sine only has one option, and that's a 2 times sine times cosine. There's no cosines in here, so it must be cosine. So I'm going to try and rewrite this so that it is cosine of a doubled angle. And the reason I know that, right, is because first of all, the angle here is a single angle. And so if we look back at our formulas, so I'm going to scroll up and we're going to look back at our formulas for cosine. And I see that the double angle cosine formula that has only sine squared is a 1 minus 2 sine squared. But here I have 4 minus 8. Well, that's easy because we can factor this, right? We can factor out of this. We can pull a 4 out. When I pull a 4 out, I get 1 minus 2 sine squared x. Well, that's exactly cosine of 2x. Okay, so when we're looking at this, we're trying to figure out, okay, because we were told to use double angle formulas, I'm like, cool. So I've got sine of 2x is 2 sine of x cosine of x. Tangent of 2x is tangent, or 2 tangent x over 1 minus tangent squared x, right? So both of those are there's just one option. But cosine, there's 3 options, and they're all involving squared trig functions. And so looking at this, I see I have sine squared. I know I have to use the cosine double angle formulas. I just have to figure out which one and how to make it work. And it is almost always as simple as factoring a number out. Like in this case, we factored out 4. It may be a more complicated expression, right? What if we had something like 4x squared minus 8x squared times sine squared x? We factor out a 4x squared, and we still end up in the same space. Okay. Now we look at this last one here. We have 6 sine x times cosine x. Well, the only formula that involves a sine and a cosine that aren't squared is for the sine of a double angle. But the problem is that is 2 times sine of x cosine x. This is 6. But that doesn't mean we can't deal with this, right? How can I change a 6 to a 2? By factoring out 3. So if I factor out a 3, I'm left with 2 sine x cosine x, which is exactly sine of 2x. And so that's it. That's all we're doing here, right? We're really keeping this kind of simple. And I don't want to do too much crazy stuff. We're not going to kind of over complicate these things. We want to keep easy. So let's use double angle identities to evaluate the following. This is going to require a little bit of some tricks from the past with these new skills of today. And so anytime we have an inverse cosine of x, we know that's going to give us back out an angle. And so it's always nice to kind of go, okay, cool. So we're going to say, let's let inverse cosine of x equal theta. So since inverse cosine of x equals theta, that means then that cosine of theta equals x. Okay, if cosine of theta equals x, then I know I can find the other parts. Because when it's just x, we can think of that as x over 1. So I can create a triangle, right? Because cosine is adjacent over hypotenuse. Now, I don't know where this is at, which quadrant it's in. But what I do know is that x is less than 0. Okay? So, if x is less than 0, let's just look at this. So that means that this right here is x, this right here is 1. So then we go through and we do some fancy Pythagorean theorem. A squared plus b squared equals c squared, and we end up with this side here is the square root of 1 minus x squared. Okay. Now, you may wonder, well, why isn't this angle, if x is less than 0, why isn't this angle down here? Right? And that goes back to the domain and range of cosine inverse or inverse cosine. If you remember, inverse cosine was used from 0 to pi. So that is why it has to be in the second quadrant, because where inverse only gives us an angle back in 0 to pi, right? It wouldn't go back over here. And so because x is negative, has to be here. Okay. So like I said, we're reaching back, using some information from the past, applying it into these new situations. So now what we have is that inverse cosine of x is theta. So that means cosine of theta is x, which means we kind of get this triangle here, right? And this x value is a negative number. Okay. So if I look at sine of 2 cosine inverse of x, I'm going to rewrite that as sine of 2 theta. Because we said cosine inverse of x is theta. Well, sine of 2 theta is 2 sine of theta cosine theta. Using our triangle, we get that sine of theta is the square root of 1 minus x squared, and cosine of theta is x. That's it. Now, if you want to kind of do some rearranging and make it a little prettier, right? Usually we put all of our non-rooted pieces together in front and then have our root there. But either one's fine. Okay. Now, we're going to do an exactly similar thing with cosine of 2 tangent inverse of x. X is greater than 0. So remember that inverse tangent, okay, is only applied from negative pi over 2 to pi over 2. So that means this angle is going to be either in the fourth or first quadrant. Since x is greater than 0, okay, we are going to be in the first quadrant. So again, we're going to say let tangent inverse of x equal theta, which means tangent of theta is equal to x. So that means our triangle, our angle in the first quadrant, okay, tangent is opposite over adjacent, so x over 1. So that means our hypotenuse here is the square root of x squared plus 1. Okay, so doing a lot here, right? We're just saying let tangent inverse of x be some angle theta. Since inverse tangent is defined only for these angles and x is greater than 0, okay, we are in the first quadrant because that is where tangent is positive. Okay, so since tangent of theta equals x is greater than 0, we are in this first quadrant. Okay. Now, cosine of 2 inverse tangent of x is cosine 2 theta because we let tangent inverse of x be theta. So now we use the property of double angle identities, the double angle formulas, to say that this is equal to 2 cosine squared theta minus 1, which is equal to 2 times 1 over square root x squared plus 1 minus 1. Oh, this is squared. Sorry about that. So this becomes 2. You square root, it just becomes x squared plus 1 and minus 1. Now, if you were to try and combine these, it would work. You could do it. What you end up with is nothing really that pretty. You end up with 2 minus quantity x squared plus 1 over x squared plus 1, which then combine like terms, you end up with 1 minus x squared over x squared plus 1. Okay. It's kind of fine either way, wherever you want to stop at, but just kind of knowing what's happening there. All right, so that is double angle identities. So that's taking the trig function of a doubled angle, so some angle that is being doubled, and being able to work with that. And all that really is doing is it's just kind of applications of the sum formula. Now, power reducing formulas. Power reducing. I don't really want to dive too much into this. What this really builds off of is the cosine identities. So if you think about the cosine identities, let's go all the way back up. Okay. Cosine of 2u equals 1 minus 2 sine squared of u. If we solve this for sine squared, what we end up with is cosine of 2u minus 1 divided by negative 2. If we change the signs on those, we end up with 1 minus cosine of 2u over 2. And that's exactly what we end up with right here. Okay, so that's all that is it's just taking those and manipulating them. Same thing for tangent. We had a tangent squared in the double angle formula for tangent. And so if you just manipulate that, this is what we end up with. Again, I'm not worried about you guys figuring out the minutia of where these formulas come from. I really just care, are you able to plug and play with these, right? Are you able to work with them? So find the exact value of sine squared of 165 degrees. Just use the formula. So sine squared of 165 degrees is equal to 1 minus cosine of 2 times 165 degrees all over 2. Cosine of 165 is, 2 times 165 is 330 degrees. Cosine of 330 degrees is root 3 over 2. So we get 1 minus root 3 over 2 all over 2. Now, a lot of things you could do here. Combine these, multiply by reciprocals, and so forth. And in the end, so I'm going to leave that up to you. What I want you guys to do is to figure the steps to go from here to our next step, which is the final answer of 2 minus root 3 over 4. Okay? That's it. Right? Again, I just really want you guys to focus on simply applying these formulas. We're not getting insane craziness with these. Really just, I want to keep it simple. Okay? So, example 7, we want to rewrite using a power reducing formula in terms of the first powers of cosine. What in the world do we mean by the first powers of cosine? Okay. What that means is we want to write these so that we have a cosine to the first power. So in other words, simply a cosine of something. Okay. Not cosine squared, not cosine to the 15th, just cosine. So cosine squared of 6x, well, that's easy. I can just directly apply the power reducing formula, which said that cosine squared of u was equal to 1 plus cosine of 2. And in this case, our u is 6x, so it's 2 times 6x all over 2. Now, if you want to simplify that, right, we can very easily 1 plus cosine 12x over 2. No further simplification is needed on that. Now, how do I deal with this next piece? There's two ways you could do it. And the easiest way is to break this up. So cosine of 4 to the fourth of x is really just cosine squared x times cosine squared x, right? If you remember your exponent rules, right? If I have b to a power times b to another power, we combine those exponents by adding them together. So the bases are both cosine x here, and so we just add those exponents. And so here I can just apply the power reducing formula twice, giving me 1 plus cosine of 2x over 2 times 1 plus cosine of 2x over 2. Now, what do I do? Well, I need to combine these, simplify, right? To do that, I just multiply straight across. So my denominator is easy. That's just 4. But my numerator, I have 1 plus cosine 2x, 1 plus cosine 2x. So I need to distribute. And when I do that, I get 1 plus 2 cosine of 2x plus cosine squared 2x. Dang it. Ended up with this another power of another squared cosine. So we're not done yet, right? Because we have to write this in terms of the first powers of cosine. Almost there, but we got to eliminate this last guy. And so bring it up here. 1 plus 2 cosine of 2x plus 1 plus cosine of 4x over 2. No triangles. Over 2. All over 4. So what do I do here? Well, I need to get rid of that fraction in the numerator. And the easiest way to do that is to multiply by 2 over 2. So I'm just multiplying by 1. But what's going to happen here is this 2, when it distributes in, so I've got to distribute across, when it distributes into this fraction, it cancels out. So what I'm left with is 2. What I'm left with is 2 plus 4 cosine of 2x plus, now that 2 got distributed into this fraction, but that denominator just canceled, so plus 1 plus cosine of 4x. And then my 4 gets multiplied by 2, giving me an 8. I'm not done yet. And the reason I'm not done is because notice I have this 2 and that 1. Need to combine like terms. So our final answer is 3 plus 4 cosine 2x plus cosine 4x all over 8. Now we are done. Whew. I like cosine to the 4th of x better. This is just a practice. This is just an exercise in applying the power reducing formula here. This is not something I'm going to really test you on. I'm not going to give you a test and say, write cosine to the 4th of x in terms of cosine to the first power. This is just kind of a messy algebra problem. It's a really great practice, and I really hope you guys, if you don't understand what's happening, go through and do it yourselves. Take the time to practice this. It will make your algebra skills better. It'll make your trigonometry understanding better, and it will make you a better mathematician. So for those of you who are going on to further math classes, especially if you're going to be in Math 251, you will need to know this. So, well, you need to know the skills behind this, not necessarily that cosine to the 4th of x equals this fraction. So there's power reducing. We're almost done. Almost done. The last one we're going to deal with is half angle formulas. Okay. Half angle identities. And these are just dealing with, instead of double angles, we have an angle that's cut in half. And this is really simply looking at these power reducing formulas. Okay. And solving some messy math. I don't really need or want, actually, I don't really want to go into solving or deriving these. I just want you guys to look at them and go, yes, that's what these are. You may be like, I have no idea where these came from. I need to know where they come from to be able to use them. But I just really want you guys to recognize that the importance here is that you guys are able to think through the application process, that kind of critical thinking of figuring out what these angles need to be. So like for this first one, determine the exact values for the sine, cosine, and tangent for the angle theta equals 11 pi over 12. Now, if you remember, our very first problem in 7.4 was to find sine, cosine, and tangent for 11 pi over 12 using angle sum and angle difference. We used angle sum in that problem. But now I want to do it using half angle identities. And so what I have to do is I have to figure out, okay, if theta equals 11 pi over 12, I need to figure out for theta to equal that, what does u over 2 need to equal? So if theta is 11 pi over 12, what is u? I'll just multiply both sides by 2, and I get 11 pi over 6 equals u. Okay. So by figuring these out, so sine of 11 pi over 12 is equal to sine of 11 pi over 6 over 2. Well, we are going to figure this out. But before we do, notice that for sine and cosine, we get this plus or minus. Well, that depends on where our angles are. Okay. So if we look at where theta is 11 pi over 12. 11 pi over 12 is not quite all the way to pi, so it's somewhere in here, which means sine is positive, cosine is negative, and tangent is negative. So when I'm doing my sine of 11 pi over 6 over 2, I need to choose the positive version. I'll put that in red because that's kind of more of a note. And then 1 minus cosine of 11 pi. It's very hard to draw straight lines on a computer like this. 1 minus cosine of 11 pi over 6 all over 2. So cosine of 11 pi over 6 is root 3 over 2. So we get 1 minus root 3 over 2 all over 2. Okay. Just like before, we're going to use this weird sneaky little trick. Multiply in here by 2 over 2. And so what we end up with is the square root of 2 minus root 3 over 4. Okay. And if you would like to, you could further simplify this to be the square root of 2 minus the square root of 3 over 2. And what I did there is I just split the square root. So we'll do some scratch work. Square root of a over b. Not scratch work, just refresher. Right? So if I have the square root of a fraction, or square root of a quotient, that's the same as the quotient of the square roots. And so by doing that here, we can take square root of 2 minus root 3 over 4, take the square root of the numerator separately from the square root of the denominator. Since 4 is a perfect square, we get 2. This step is not necessary, so I'm going to just kind of circle it because it is not a necessary thing to do. If you do it, that's great. If you don't do it, that's fine. It really doesn't matter, whatever makes the most sense. So let's move on. Cosine. We now need to figure out what cosine of 11 pi over 12 is using these half angle formulas. Okay, come on. Here we go. Cosine of 11 pi over 12. Cosine of 11 pi over 6 over 2. Now, as we stated with where this angle is, cosine is going to be negative. So that means we're going to choose the negative version. This time it's not just kind of symbolic. We have 1 plus cosine of 11 pi over 6 over 2. Now, if you notice, the only difference between sine of u over 2 and cosine of u over 2 is that it's 1 minus versus 1 plus. So we can use all of the work we just did to save us some time, and negative 2 plus root 3 over 4. Okay. And that's it. Tangent 11 pi over 12. Tangent of 11 over 6 over 2. Using that, which one do we want to use? Doesn't really matter. Let's just use the first one. 1 minus cosine of 11 pi over 6 all over sine of 11 pi over 6. 1 minus. So cosine of 11 pi over 6, as we know, is root 3 over 2. Sine of 11 pi over 6 is negative 1/2. Again, let's just multiply by 2 over 2 because it's a nice shortcut. And so when I distribute this 2, I get 2 minus root 3. When I distribute this 2 here, 2 times negative 1/2 is just a lovely little negative 1. So we just distribute our negative sign and we end up with negative 2 plus root 3. There we go. I'm going to start this next one, but I don't want to do it. Why? Quite frankly, I'm tired. These are not the most fun problems to do. So what I know is I know that tangent of theta is negative 5 over 12, and I know this. What that tells me is that theta is in the fourth quadrant. This just tells me that theta is in quad 4. So if I come over, get this angle here, create my triangle. Since tangent is opposite over adjacent, we get negative 5 over 12. Now you may wonder, why is this negative 5, why is this 12, right? Well, look, it's on an xy axis. That's why it's negative 5 and the 12. Use the Pythagorean theorem, and we get that this is 13. So now, fix a little typo here. These are not used. These are thetas. Okay. So to find sine of theta over 2, just apply our function. We know that in this quadrant, theta is going to be negative, or sine is going to be negative. So we have negative square root of 1 minus cosine of theta over 2. And I'm looking at my answer key. Oh, I forgot about that. Back up. That's not what I wanted. This is what I wanted. Okay. This is why I wanted to set this problem up. So we're in quadrant 4. We use blue for our hypothetical possible thetas. Theta could be barely in quadrant 4. And so that's greater than 270. If I cut that in half, okay, that is going to end up in here. If it's super big, it's going to end up over here. So either way, theta over 2 is in the second quadrant. So that means So theta over 2 is in quadrant 2. So that means when I'm looking at doing sine of theta over 2, I'm actually going to be choosing the positive version. And I'm just doing this problem. 1 minus 12 over 13 over 2 multiplied by 13 over 13 square root of 13 minus 12 over 26 is equal to 1 square root 26. Or root 26 over 26, if you like. Cosine of theta over 2 is going to be the negative 1 plus cosine of theta over 2. So instead of getting 13 minus 12, it's going to be 13 plus 12 over 26, which is going to end up giving us negative square root of 25 over 26, negative 5 over root 26. So it becomes negative 5 root 26 over 26 is our final rationalized answer. I don't want to do tangent. You do tangent. I'll give you a clue. Tangent of theta over 2 is negative 1 fifth. So there you go. I'm tired. You're tired. Skip. That is not a circle. That's a P. Skip. 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 All right, now do these last. I'm just kidding. Skip. Skip it all. Skip everything else. I don't want to do it. You don't want to do it. It doesn't matter. It's the exact same thing, just different formulas, just plugging, playing, manipulating. I have a feeling you guys are going to have plenty on your plates with these two things. So that's it for lesson 7.5. You guys have been great. I will see you guys next time. Section 8.1. We're going to have some fun. That is where we get into some fun applications of trigonometry into the real world. So for those of you who are like, when are we going to ever use this? 8 is where we're going to start to see where we can really use this stuff. See you guys there.